2009 because we started working on droplet impact and discovered the historic work of Yarin and Wright. We had a chance to discuss the work of with Sasha several times today. And so eventually I met Professor Yarin, and then I learned that he has actually many interests which are in common. Professor Yarin comes from the Institute of Physics of the Russian Academy of Sciences, where he worked under the advisorship of Professor Librovich, is that right?
Librovich,
and Professor Gunshot. And then he moved to Israel and then to the University of Illinois at Chicago, where he's now, and he's going to talk to us about atomization in high-speed and high-power applications. You'll be to stay a little while after the seminar if you want to talk to the team at the end of the seminar. And not much more to add, so please, Professor Yarin.
Well, thank you. Thank you for your kind introduction, Professor Walewski. It's my pleasure to give a talk in Sorbonne. That's like a very important word for me, obviously. So, and like the topic is atomization in different situations. And essentially the common ground will be atomization driven by acceleration. Okay, so all these, topics I'm going to cover would originate from acceleration of fluid. So this is a work supported by the National Institute of Justice, so the Department of Justice in the United States. It's a regular granting agency in the United States, and it's a continuous work already, for quite a number of years. So what is like the first topic? The first topic is forensics. So forensics has a question like that. So you have an individual who was shot, killed, maybe. Okay, and there is a blood spatter coming this way, which is called back blood spatter towards the shooter. There is a forward blood spatter, but I thought forward blood spatter is less interesting because there is a bullet there. So, and the question is, what was the position of the victim, and what happened? So police today uses the following method. So by the ellipticity of blood stains, I'll show it later, you can establish the mole as the impact angle. Then they just plot a straight line, and the intersection of the straight lines is considered to be the origin of blood. So definitely this method neglects gravity and neglects air drag, and typically, this situation leads to missing by 1 meter, the origin of blood, and based on this type of evidence, which is called blood pattern analysis, BPA, people sometimes are sent to prison, for life. Okay, so I have letters from these people. So then the question is, can we do better, and what happens? So I started working on that accidentally. I had a flight from Chicago to Frankfurt, and I watched a movie which is named Phil Spector. So Al Pacino plays, Phil Spector, and Phil Spector was the most famous, musical producer. Okay, some people already know him. That okay, the guy who made Beatles, the Beatles. In 2002, he invited a waitress, an unsuccessful actress, essentially, to his mansion in LA. And in a while, he showed up and presumably mumbled something, that I probably killed somebody. Then, police came and they found the woman, sitting in a chair and killed by short range, shooting in the face, close to the mouth. And okay, then he is taken to the court, and everyone hates him. He's a billionaire, he's a junkie, he's whatever, exotic. But in the movie, there is one moment where and that's a reality essentially. His lawyer organized a forensic experiment, And the forensic experiment is like that. There is a mannequin filled with swine blood and shooting, and there is the outfit of Phil Spector. That's the type of outfit. So that's his real outfit, essentially. Okay, so you can imagine, what kind of like a guy that was. And in the movie, there is very pictorial, two-face, blood flow, like slow motion, and everything is covered with blood. And in reality, it was clean. So these are all markers, presumably finding, microscopic, droplets. So when I watched this movie, I submitted a proposal, to these guys. Essentially, it was very nicely taken, all people, I described the case as like my trigger, and all reviewers, wrote that this guy has a very good understanding of forensic whatever, like he talks about real case, and they delivered, $1.5 million for that, okay? So that was the first proposal. So that's my trigger to this work, and at that time I saw that Phil Spector is not guilty. He was sent, but then he quarreled, with the lawyer, had another lawyer, and that landed him to prison, and he died in prison. But I thought he's not guilty. So and then I started, searching essentially what is available, and Michael Taylor from New Zealand was the leading person, who accumulated a lot of experimental data. And can we, somehow put shades down if possible? These are targets, filled with blood, and the bullet is coming this way. So you see forward shooting, and you see also you see forward blood spatter, and you see backward spatter. So I thought, first of all, it's interesting to deal with the backward spatter. So then I saw that this essentially should be like, what's the physics of that? Because after all, if you want to predict, droplet motion or whatever, you need first of all to know the size of the droplet, the initial velocity, and this is determined by the physics, how the spatter is formed. So and I thought this should be a typical case of the Rayleigh-Taylor instability, because you have a denser fluid, which is blood, accelerated towards lighter, which is the air, and should be Rayleigh-Taylor. So just to remind you that Rayleigh-Taylor instability is typically discussed, in relation to gravity as an acceleration. And then you have a situation when you have a denser liquid, which is a puddle of water, and the gravity is directed towards the denser. So this is stable, and the puddle is stable. On the other hand, if you have water on the ceiling, okay, so then the gravity is direction of the wavelength. So you can find the spectrum, linear spectrum, and the main result is here. So the wavelength, the characteristic wavelength, so the size of the droplet essentially, is related to surface tension, density, and gravity, acceleration. But in the context of the Rayleigh-Taylor instability, it might be any acceleration. So it shouldn't be inevitably gravity acceleration. So then the question is how to predict this acceleration in our case, which is shooting. Resolve and get some information from this type of experiments, and we did some analysis of that, going forward to the prediction of this blood spatter analysis. So essentially, this is the area where you can already resolve individual droplets and try to, for example, do PIVs based on these movies. No one did it. The police accumulated quite a lot, but no one did. By the way, there are some references with my collaborators and PhD students mentioned here, so you can take a look in detail if you want. So we try to analyze, what happens. And there are also a lot of data on forward spatter, but I told you that forward spatter is less interesting because the bullet is typically available, and by the bullet you can reconstruct what happened. However, it appeared to be not necessarily the case. In many cases, they told me that bullet is unavailable, and then we also worked on forward spatter. But today I'll mostly concentrate on the backward spatter. And also, there is an interesting thing which came to my mind a little bit later, that there is interaction with muzzle gases. So essentially, when you shoot from a gun, so there is products of combustion, released from the bore, And this makes, as I'll show you later, vortex ring which moves forward, and if you have a backspatter, so they, collide with each other, and many things could happen. And this is visible, for example, in this set of images where the back blood spatter is essentially shifted aside by the oncoming bullet, by the oncoming residual gas. So the first thing I thought, to do fluid mechanics, I thought slender bullet, because it's easy to do fluid mechanics for slender bodies. But people told me slender bullets are not in fashion today. People want, blunt bullet. It makes much more harm, so forget about that. But then I visited Sydney, and this is downtown Sydney. There's a monument, to the glorious Australian past, So I thought, no, I'll do the first, the slender bullet. So then the slender bullet is a very easy case, because it's essentially like Wagner-like problem. Wagner did in 1930s, he did penetration of a wedge, because it's a very short range motion. So then the potential theory is okay. You can neglect all viscous forces and whatever. So essentially, you can find the potential. Like this is a solution of Laplace equation, technically speaking, for the axisymmetric case, but you need to find the distribution of sources, which create, by the boundary condition, the body. And for a slender body, it's very easy to do. That's a boundary condition, which immediately determines you the distribution of the sources by geometry. So I'll skip all the details, elementary, and you end up already with known sources, and then you have the potential. So using this potential, you can find the flow field, and you can find the main thing. You can find, essentially, you can calculate the velocity field and you can find acceleration towards air, okay? And the acceleration towards air, that's exactly what you want, because this is Rayleigh-Taylor instability, and the droplet size is determined by this acceleration, and also the initial velocity is determined. So then you know everything, to proceed with, let's say initially I started doing like two-phase flow, so droplets form the second phase, interacting through drag force, with the first phase, which is gas. Suction goes by the Schlichting submerged jet, and you solve the dynamic equations more or less standard way, and then you can essentially find where the blood droplets are deposited. So before I'll go to the predictions, I want to analyze the experimental data I showed you. If you take a look, there are two sets. The red symbols are for the forward spatter, and the blue for the backward spatter. What is non-trivial here is the fact that velocity of droplets increases initially when they move in air, in spite of drag force. Okay. So what was the reason for that? The reason for that is in the collective effect. Okay. So if you see this V formation of birds know pretty well, that the leader forms drag force, the wake, and the wake essentially pulls, forward the others. So it's very easy to fly in the wake. They change. So dolphins also understand it. That's how they demonstrate, that they can swim faster than a military cruiser, because they stay most of the time in the wake. So the cruiser is pulling them, and from time to time they move around. Okay, so they are smart, and droplets do the same thing. So, and we accounted for this in the calculation. So you have to account for that. Now, what are the typical experimental data? This is the set of blood stains. Essentially they analyzed through their ellipticity. If you take a look at this, so ellipticity is very far from these assumptions. So the experimental data is essentially pretty dirty, I would say. And the experiments are done by not your group, but by a special facility where a policeman is just physically shooting. So even a repeatable experiment is essentially not repeatable, because the policeman is just shooting, as he wants. Okay. So this is a set of comparisons of predictions with experimental data, and I'll have a little bit better because this was done before I even affected the experiments. So typically, what you get from the experiments, you have an average number of drops, for example, on the floor, at the distance from the victim. You have the average area of the droplets, and you have some cumulative data. So the red dots are the predictions here. So you see that they go like in the middle of this, noisy experimental data, and that's how it is. Okay, so I cannot claim, better than that, but I'll show you a better comparison with experimental data. That's another set of shooting, and you can, and I want to show you with comparisons with the predictions, and I want to show you, for example, this case. So these are two experiments presumably being repeatable, okay, but the data is completely different. Therefore, like predictions, like comparison of predictions with that, you can say something. Comparison of predictions with that, you can say that it's very bad, but essentially it's not very clear what is good and what is bad. And that's how it stands. So you can also predict, distribution in widths. So you have blood droplets, propelled, in all directions. So you cannot definitely calculate all of them, but you can, calculate some of them, and you can find like an envelope of this, the length of the envelope. So these are the predictions, on the, like once again, superimposed on the experimental data from two sets of experiments. So you can say more or less you are in the middle, you can say that no, you are not in the middle at all. So that's how it stands. So anyway, I'll switch now to the fashionable bullet, okay? That's a bullet they like, okay? This bullet also can be, treated essentially. This is the case of the so-called like impulsive motion fluid mechanics. So when you have, an impulse delta p, which is very large, applied for a very short time, so then the integral of one tends to infinity, another tends to 0. So the integral is of the order of 1, and this integral serves as a potential. Okay, so this is a well-known thing. Essentially, in the 1930s, that was a very powerful theory for skids of seaplanes, landing. So like where you have to predict the impulse. So the impulse is essentially potential. It becomes a potential flow irrespective of rheology. And then you have the initial conditions. This blunt bullet, hits a circle, okay, with a given velocity. All the rest is free of impulse, and you have to solve such a Laplace problem. You can do it essentially. I'll skip over the details, and after solving and finding the velocity field, you find once again the acceleration. So the moment you know the acceleration, you know the droplet size, and you know the droplet velocity, and you can talk about like blood spatter. So one additional thing I'd like to mention is that the bullet approach velocity, which is denoted VA here, is different from V0, which you have to take for the initial velocity of the impact. Why? Because at the moment of the impact, there is a formation of compression waves, which take away some energy. And essentially, this problem can be completely solved, very accurately. It reduces the approach velocity to the real impact velocity like that, depending on the mass of the bullet. So the difference is from 1,000 meters per second to 988 in this case, but it should be accounted for if you want to be accurate. So I'll skip over like the spreading of the spray itself, which also can be predicted and pretty accurately. And now I'll show you like much better experimental data. So when I saw the original experimental data, I definitely been unhappy. So then I worked with these people, who do experiments, and there were sets of experiments which are called T13 and T14 in this case, which were much better done. Much more accurate, and here you see the comparison of the average stain area. In the screen was standing before the target, so essentially shooting was through the screen, and the blood stains were collected on the screen as a backward. So in this case, you see the distribution of relative to the radial position from the bullet. Okay, so this is a much well-defined experiment, and here the agreement of the predictions is not bad at all with the experimental data, and the experimental data agrees with itself not very badly, I would say. So here the total stain area, once again, the versus the distance, so the maximum is predicted pretty accurately. So you build some confidence in this type of predictions. This is the impact angle. predicted, I'll skip this over mostly, the average Weber number, the impact, can be predicted, and so on. So this is the first thing, still where I saw that Phil Spector is not guilty, and essentially I even thought, maybe we'll release him after all, from prison. But then I started thinking about like muzzle gases. And once again, Michael Taylor did these experiments, and you can see here, this is the data coming on the scale of like microseconds. So what I showed you before, this blood spatter, whatever, is on the scale of milliseconds, and this is microseconds. So here you see a set of, first of all, two types of shock waves. One oblique shock waves, this is a bullet, oblique shock waves are visible. And then this is a von Neumann-Teller set of, like self-similar shock wave propagating, which you see here. Okay, and only after that you have, muzzle gases are released. And these muzzle gases form turbulent vortex ring. So I wanted to describe this turbulent vortex ring and to consider the interaction of this vortex ring with the blood spatter. So that's essentially the setting you are talking about, and let's talk about like propellant gases. So this type of, this is a free turbulence. So the free turbulence is described very nicely by Prandtl's semi-empirical mixing length theory. It's a well-known fact. So I used that theory. So the kinematic viscosity, this is essentially the eddy viscosity standing here, which is related to the radius of the vortex ring and the velocity of the vortex ring and the empirical coefficient, which is found from a single experiment. Okay, and then you just use it. So essentially, it's more convenient to write this problem in the vorticity terms. So this is like an equivalent of the Helmholtz equation, for omega vorticity. And then you have vorticity and the stream function, the two equations you solve together. So without the right-hand side, this would be just a Helmholtz equation, but otherwise it's like a modified. So then it appears to be that this is a self-similar problem. If the bore is much smaller than the distance you're talking about, so then it's like formation from a single point, however, with a finite hydrodynamic vortex impulse, okay? So this is an integral invariant of these equations, okay? And essentially, in the case of shooting it, it's a given scalar, okay? So related to the, and you don't care about like the real formation, you go like with always self-similarity. So this is self-similarity of the first kind, I would, insist, like, which is found just from dimensional analysis, how things depend on parameters, and then you reduce to this two-dimensional problem, which strangely, with one simplification, okay, there is an integral condition, obviously, this impulse, the boundary conditions, and with some simplification after that, it appears to be a problem identical to the cylindrical quantum oscillator, okay? So with choosing rules and whatever, so you do essentially from this line, you do quantum mechanics, and you end up with this solution, okay? So this is an analytical solution for this turbulent vortex ring, like the stream function and the vorticity are given there as a functions of all the parameters, including time. And the empirical coefficient, after all, reduces to this type of equation. So essentially, one comparison with experimental data produces you the empirical coefficient, and then you go with that, with all the other calculations. Now, this is the flow field, the axisymmetric flow field, so you can find all the details, in the publication. Okay, you might wish to find, the exact center, which is like limit of that situation. So it's all doable. So this is the final result. So the vortex ring, propagates, with this velocity as a total, entity, depending obviously on the empirical coefficient. So essentially, one set of images, immediately produces you the empirical coefficient, and you can do comparisons with experimental data. So essentially the comparison is pretty good. This is the data which existed in the literature before I started doing this. This is the data already now working or done in like in comparison with the theory in parallel experiments. So you see propagation in time, several shootings. I essentially have quite many. Okay, we do not necessarily follow the leading edge, but for some to some extent, we are not missing that much. So it looks like that this general fluid mechanics is like okay. Now you can also think about like multiple vortex rings, because sometimes you see some weapons release several vortex rings just because of their construction. So this is a couple shown here, predictions. Okay, and then what is the effect of this vortex ring on back blood spatter? Now what do you see? So the red distribution number of stains per distance from the victim, like in two cases where you don't have interaction with the vortex ring, and when you have interaction. So when you don't have, you have these gray bars. When you don't have interaction, these are gray bars. When you have interaction, everything essentially, is significantly pushed back in this case. However, several droplets are propelled, much forward, okay? So this is a kind of like an average description. However, then I wanted to deal with individual droplets. Let's see scenarios, like an individual droplet propagates, no effective gas. So these are typical, predictions. So without interaction with muzzle gases goes this way, with interaction with muzzle gases, pushed forward, pushed backwards, sorry. However, there are very interesting cases available, when the droplet is not only pushed backwards, but it goes around the victim and lands behind the victim. So that's how it goes. So, and we predicted that, and then experimentally it was found, okay? So that's the explanation how Phil Spector was guilty, and how he was clean, after all, because luckily, his shooting position was that way that all the droplets, went around. Okay, so this is possible, and this is a forensic experiment, okay, which led in reality to suspended jury, essentially, wasn't that convincing, and like being an expert going against that, I could land him in prison earlier than he went there, but I didn't want to do that, obviously. Okay, so these are some predictions. Okay, so we have a bunch of cartoons which illustrate, what I told you. So this vortex ring propagated, and a droplet appears, and this is a bigger droplet, it goes through so it's decelerated by the vortex ring, but still goes forward. Now, another scenario, this is a droplet after the secondary breakup, which I'll mention later, a smaller droplet. Vortex ring goes forward. These are predictions. And suddenly a droplet appears, okay, and this droplet is picked up by the vortex ring and pulled back, okay? So it can go around, as I told you, so quite standard situation. So then detailed experiments were done by James Michael in Iowa, and he observed directly, like interaction with the vortex ring and turnaround of droplets. So this is quite realistic, I would say. Now, a comment about this ellipticity issue. So this is droplet coming and makes an elliptic stain. So the police, uses this sine angle, to define trajectories. If you take a look at the sine values when the angle changes from 75 to 90, so that's the range of the sine. So accuracy of this method, like is nil in the range of angles from 75 to 90. So there are multiple other things, like spreading. I'll say a little bit. I'll tell you a little bit about like spreading on carpets. That's of interest for me. Like, all right, you delivered blood, so then you have all this. We made a program which analyzes all these forms, but I'd like to show you this. So we produce a lot of nanofibers. This is another activities in my lab. So nanofiber mats, we do them for different reasons, but we also study droplet interference with them. So if you put slowly a droplet on this nanofiber mat, and the material is pretty wettable, like contact angle of this polymer would be of like a plane would be 30 degrees. So essentially, it sits. This droplet sits as a like super hydrophobic material because it's mostly air, and by Cassie-Baxter it should be like non-wettable. However, if you drip a droplet on this surface, so there is no bouncing back, there is nothing. The droplet makes a stain which doesn't retract at all. Okay, and the reason of that is that you have the phenomenon which is called hydrodynamic focusing. Okay, it's essentially known in the shape charge jets, but here it works exactly the same way. So you have the droplet is essentially 1 millimeter. It's big. Pores are sometimes in 10 microns. They are much smaller. So all the kinetic energy this droplet brings, is propelled in one or a few pores like that. So the propagation inside, you can calculate it using complex analysis exactly. So this is the result. So that's the velocity of penetration in the pore, and that's the droplet velocity. So this is of the scale of 1 meter per second. Whereas there is a factor of the drop size to the pore size, which might be 100, which might be 1000. Okay, therefore the velocity of penetration is dramatically higher than any wettability-related Washburn-Lacus effects, and wettability doesn't play any role at all. We did nanofiber mats from Teflon, which is almost like super hydrophobic, and we can deliver droplets of water very easily inside. By the way, I didn't tell you, if you have questions, please ask me, interrupt me, okay? Don't be shy. Okay, so I'm going like... So, okay, I told you that this type of problems can be easily solved, okay, using conformal mapping and a Poisson integral, by the way, okay, a very important, technique, so solving boundary value problems for Laplace equations. So that's the result I already showed. You can do also the axisymmetric case, like using the most standard technique. So these are the predictions of the like complex analysis. This is the distribution of pressure effectively. Okay, so we see the pressure, the orifice is very high. Okay, this pressure drives, so the entire, droplet is driven to the irrespective of wettability. Now, this is the axisymmetric case. You do it by different technique, but the factor is even larger a little bit, obviously. Okay, so then that was submitted for publication, and one of the reviewers, I suspect an American, would does not believe in any predictions, he wanted to see data. Okay, so we did experiments, droplets dripping onto suspended membrane of nanofibers. Okay, and we measured the ejecta coming from the filter, essentially. So what happens here is the following. The droplet is approaching at velocity about 2 meters per second, okay? Now, the jets coming from the pores coming with velocity of 7 meters per second. And this is in spite of the fact that you have a lot of losses, viscous losses inside and so on, okay? What's the reason for that? Exactly that. So you outflow even faster than you inflow because of the hydrodynamic focusing. Okay, so this is a direct proof of that. So this is all described in more detail. We published 2 books in Cambridge University Press. So some on fiber, some on drop impact, but you can find them and see the details. Now I'm turning attention a little bit to non-Newtonian fluids. So essentially, it's well known that blood is non-Newtonian. And essentially, we discovered, and then we found that some other people discovered it before us, blood is even viscoelastic, okay? So essentially, there is elasticity in blood. So then it means that when you have a droplet formation, droplets are disconnected from liquid body. So there is an elongational flow, and elongational flows develop dramatic, elongational viscosity because of the coil stretch transition, which was discovered in this university by Dijon, 1974. So that's exactly what happens. So this is an experiment with saliva, by the way. Saliva is also viscoelastic. If you do shear flow with saliva, shear measurement viscosity of water. If you do this type of experiment, viscosity is 10 to the 4 times that of water. So these are elastic effects, okay, which stabilize fluid. So these are experiments with blood already, okay? So shear thinning in the shear. However, dramatic elongational effects, formation of the thread, and as a result of that, you see a lot of ligaments, in the blood dripping, which is viscoelasticity. Okay, and you see this is a very fashionable tool today. In addition to like blunt bullets, people use more and more hammers. So 13% growth of hammer killing in the United States the last year. So this is blood dripping from a hammer, and also this long ligament is elasticity. Okay, so you can do estimates. I'll skip over. So elasticity is important. And people essentially try to use elasticity. For example, firemen, added polymer additives and suppressed atomization. Okay, as a result of that, the jet is propagating much further. Okay, and napalm in flamethrowers plays the same role. So now I'm switching attention to a totally different phenomenon. But related, okay? It happened, when they announced a lockdown in Chicago during COVID, like the beginning of COVID, essentially. And the College of Dentistry, which is very powerful in my university, was scared because they have a hall where 30 people should sit with open eyes, or open eyes obviously, but open mouths, and a scaler, Cavitron scaler, which is used on all of you, when they do cleaning, okay, produces a lot of droplets, and droplets are flying around, and they asked what to do, and essentially they asked my department, what to do in the sense of ventilation, how to organize ventilation. And okay, some people work on ventilation, but said, let's do like that you have no droplets at all. It's much easier, to live when you don't have droplets instead of like you are catching droplets. And that worked, very nicely. So that's the situation more or less. This is like a tooth, or the real tooth. Like this Cavitron scaler is essentially vibrating with ultrasonic frequency, about 30 kilohertz, and irrigation fluid, which is water, is supplied. It plays multiple roles. First of all, it's cooling the scaler, which is heating because of the vibrations, but also it makes, cavitation bubbles between the tooth and the scaler, which clean the deposit as it appeared to be. So it's called Cavitron. And the problem with that is that it makes a lot of in this field, they don't use the word atomization, excuse me, it's aerolization. So I have to go with aerolization from now on. So that's what you see, coming. So this is all coming from everyone. This is a CCD camera, which we used, I've been lucky, with this lockdown, my lab wasn't closed. So essentially, during the lockdown, I had a special permit, and I brought, several students worked with me, and then I brought all students under pretext that I need all of them, so I didn't have any lockdown, and it was very nice. The only thing, which bothered me that, I parked alone in the parking garage, and I saw that might something happen with me. So anyway, this is a so-called Faraday instability, okay, because of the acceleration of the scalar. And the Faraday instability produces a bunch of droplets, and you can estimate the size, and there is a lot of droplets below on the scale of like 20 microns, and I estimated the evaporation time of this, and the evaporation time of 20 and less micron droplets is faster than it settles. So essentially, such a droplet, if it delivers viruses, it evaporates, and you get airborne viruses, and the size of this virus is 100 nanometers, and there are no filters which can stop this. So that's quite clear. The question is how to eliminate that. And what I proposed is, I'll skip, several images here. What you can do, you can add, a polymer. Let me come. Probably I'll go. I'll skip several videos here, and the next one. Okay. So you can add, like water-soluble polymers, which are FDA approved, so they are used. You use or eat them on everyday, basis, and they completely, because of these elastic effects, like acting in the droplet tail when it tries to disconnect from a liquid body, they completely suppress aerolization. No droplets at all. And this is one of the demonstrations. Okay, so that's how it works. So we call, by the way, we observed this on like the very first experiment we did, and we call this Medusa. Now this is already like implemented by the industry, and the first implementation in Europe will be like this autumn. So you all will have this, like inevitably. Like you'll pay money for this, obviously. Okay, which is but this is a good thing. So essentially, you know, it was tested. You have a bunch of different polymers, you know, which can do that. You know, the United States have another approval technique. You know, this is considered to be like Europe considers this just change of the liquid, which is supplied from a bottle. So when you sit in a dental chair, so there is a bottle essentially, you know, and there is a pump, like a pipe, you know, which delivers to the tool. So, so the trick is, you know, to have a liquid which behaves exactly like water in shear, okay, and totally different from water in elongation. And that's exactly what we have here. Okay, so this pumping is unaffected at all. Now, whereas aerolization is completely suppressed. Okay, no droplets at all. So the industry, you know, which acquired this, they essentially tested much more. How does it affect cavitation? Improves essentially, as it appeared to be. How does it? And I can explain why hydrodynamically. Then how does it affect, you know, many other things like prosthesis or whatever. But one of the things, you know, they asked dentists, which already tested in Europe, was they gave a questionnaire, and many dentists wrote that this is great for women. So, and I thought, why? Okay, and it appears to be that it doesn't affect women makeup. Okay, so therefore there are some unexpected, you know, like effects here. So we call this Medusa, and okay, this is like how like it works on a mannequin. So you see the cavitron, the liquid is delivered, you know, no aerolization at all, and you collect it, you know, because you supply it, inevitably you have to collect it someplace, but no aerolization at all. So then let me show you with another polymer, okay? So just how it goes. So this like Medusa, you probably studied it at school, you know, with these hairs, snakes instead of hairs. Okay, they go all the way, but they never disconnect, and they indeed never disconnect. So this more or less, you know, the second topic I wanted to show you. Also, like, now, what is my timing? Do I have some more time, or I need to stop? Do I have 5 more minutes? Right? So another topic was like rheology. So people are interested in the like polymer rheology or whatever, and the question is like, what is the rheological constitutive equation? And all of them, you know, are postulated, essentially parachuted, you know, like from skies, and then they are used, and no one knows exactly, you know, how do they behave like in realistic situations. And the most interesting situations are very strong stretching. Okay, this is the most interesting. That's what I showed you, what happens in the droplet tails. Okay, and to test the logical constitutive equations on droplet tails is very difficult, okay, because it's not well-controlled situation. However, you can imagine such an experiment that you have essentially a cylindrical, you know, liquid body. You put inside, for example, a wire, and you put a dramatic, you know, potential, and the wire explodes, so essentially evaporates, and you have a very high pressure in the cavity, and it goes out radially, and you take imaging from the top, and then you have a dramatically strong, you know, azimuthal stretching. Okay, that's where you test your models. Okay, so that's how to do. And this is, by the way, once again, the case of Rayleigh-Taylor instability, as it appears to be, because you have, you know, a higher pressure inside compared to the outside, so this thing is accelerated, and we have seen that, you know, if you go to very significant, you know, pressure drops, so then you have, you know, an instability sets in. So then you forget about rheological constitutive equations, but it appears to be there are some other applications of interest. Some other applications are called mother of all bombs, okay, so something like that. So you want to disperse, you know, like material and immediately to ignite it. So you have an explosion which covers like square kilometers or even more, and this is like a transitional weapon, you know, of interest in some cases which I'm not going to discuss. Okay, so then you can study this Rayleigh-Taylor instability. Once again, this is cylindrical case. You can do planar case. You can do spherical case. All the equations are different, but you always can find, you know, spectrum there, and you can, you know, do predictions of like how it evolves. So this is already done numerically. So you see several snapshots, numerical predictions, and you also do experiments. In this case, it was essentially a real explosive triggering, you know, the spreading because of the other application. And I'll show you probably the video to end the talk. So this is an experiment of the type of interest, you know, the atomization on like large scales, okay, so like square kilometers, okay. So this is also Rayleigh-Taylor instability, liquid atomization, and that's the third topic I wanted to briefly mention here. Thank you for your attention, and I'll appreciate the questions. Don't be shy. Oh, that's I don't have it here. Okay, but I have no, but I can show you. Let's say I have. Let me open them. You know, the paper. That's a recent paper in the Journal of Fluid Mechanics. Let me find it. What happened? I still didn't give any talks about that, so just briefly mentioned. So this is the most recent paper, you know, we published. So about like 8 years ago, Ken Tropea showed me the experiments where a crown was formed in the drop dripping on a liquid layer, and this crown completely instantaneously disconnected from, popped up from the wall. Let me show you how the data looks like. Okay, this is the experiment they did after all. And this is a set of experimental data from Darmstadt, and you see the crown completely disconnects, flies away. So the question is why? So I worked on this about 8 years, you know, on and off, and on like I developed the theory, and then, you know, I did a prediction, and then, you know, they measured what was predicted and compared with the data. So essentially, you know, the idea is like that when a droplet, you know, impacts the surface, so whatever you have a singularity, and velocity is technically infinite, right? So the Reynolds number is infinity, and you can talk about turbulence. Now, if you do all the estimates, which I did here, okay, you essentially should show that the timing is that the entire cascade can develop there, and you can come down, you know, from like intermediate level vortices, eddies to the Kolmogorov level. So then the question is like, what will happen with Kolmogorov eddies, whatever other eddies, when they are entrained in the crown? Okay, so you have a film, and inside you have eddies. So then many interesting things could happen. And you can take a look at this from the point of view of, I'll skip all the details, you know, there are quite many. Okay, so first of all, you can predict, you know, the gut feeling is like that the crown should go away and rise and thinner, become thinner and thinner. So when it becomes thinner and thinner and thinner, it can meet the Kolmogorov range, okay? And then, this Kolmogorov eddy will just drill the wall, okay? And you'll have a hole formation there. And this is a totally different mechanism from Taylor. And by the way, this hole, and I showed, okay, let me show. First of all, you can do a very accurate prediction of the crown thickness. I developed the theory here. So these are several experimental comparisons done after the predictions. Okay, so it goes very well. The crown thickness goes down, and when it comes to the level of 1 micron, Kolmogorov eddies can drill it. Now, one additional thing of interest is to predict. Can you form holes at all? So why holes should be formed at all? And it goes more or less like crystallization theory. So there are nuclei of different holes, okay, which can appear, but some holes will grow. The supercritical holes will grow self-sustainably. Okay, the lower than that would not grow. And when you do accurate calculation of energy, which definitely Taylor doesn't consider the rim and whatever, and here it's done very accurately. So you essentially show that, there are some holes which, if you have a nucleus bigger than that, an instantaneous growth, okay? So this is step number 2. So Kolmogorov eddies triggers the holes, and the holes can grow. So then holes grow, and they grow with the velocity of Taylor-Kulik, result, which you probably know, and then they begin meeting together. So when you'll have a breakage, the breakage you'll have when you have the percolation limit reached, okay? And the percolation theory for two-dimensional continuum is fully set, and at 50%, holes, you have already an infinite cluster. So essentially can predict exactly the moment of breakage of the entire structure. Okay, and definitely, it happens underneath the crown, where it appears to be thin enough. So doing all that, I'll skip the details. We predicted the time of breakage. Okay, and the time of breakage so there is a formula which predicts the time of breakage. Okay, which is shown here, depending on all physical parameters. And this formula was compared with experimental data after the formula was derived, and the comparison goes like that. So essentially, I would say it's not bad, and more than that, it predicts you dimensionless dependence, which is shown here. Okay, you can render dimensionless. It's like natural scales, and it appears to be that there is a dimensionless number, which we call corona number. Okay, which determines the entire process, which depends on the liquid density, like in case of two identical liquids, kinematic viscosity, surface tension, and the pre-existing film thickness. Now, there are also cases where liquids are different. So I did a little bit of calculation because this is a side work, so for that case, to predict, how much, one liquid goes together with the other, because they can measure that. But I didn't develop the entire theory, further than that. So you can do it after me, okay? Because I have to do many other things. I'm sorry, okay? Right. So that's my answer to this question. Okay. But ask me questions about field specter. Don't be shy. Yeah, go ahead.
Do you think that the wetting properties of bullet or maybe hammer will affect how the slopes are studied?
Yeah, there are experiments. This is a known answer essentially, not by me. So people studied, how wettability of penetrating body affects, splash. Okay, for splash or crown formation. It does affect. However, all this data is for low speed. Okay, so maybe it's good, for hammer. Maybe I am even not certain that it's good for hammer, but definitely has no relation to bullet. Okay, so bullet will go irrespective of any wettability. So everything will be determined dynamically, and such results are available for lower speeds. Yes. And the answer is yes, wettability affects at low speed. Yes.
That rotation of the velocity is considered in
Say again? The shape of the bullet?
The rotation.
No, I don't have any rotation included. I'm sorry, I don't have it. In principle, it's not a big deal to include it, I would say, okay, but I don't have it, okay. However, I have some other results, which I didn't show here. So I have a theory for a bullet of an arbitrary shape, okay, because all this, slender body, which is a conical, or blunt, which I showed, these are simplifications, but the bullet is essentially pretty complicated, goes this way, that way. So I essentially can, solve this for any shape, okay? So I derived an integral equation which allows, to find the source distribution based on the shape without any, so this is already numerical. So this is published and this is doable. To include rotation, I cannot, at least, now, for now. Okay, other question? Yeah, go ahead. Yeah. Oh, yeah. I'll tell you what polymers do. Okay, polymers normally prevent any elongational phenomena. Okay, so technically speaking, when the question industry already bought this. Okay, so they own the main portion of that. They asked me questions about cavitation, okay, and the removal of the deposit. And I initially saw that the answer might be pretty bad for me because polymer prevents all the fast motion, so polymer would prevent cavitation. I wanted, by the way, to observe, they call it cavitron, but they never observed anything. So I did an experiment. I took a sonicator and put a sonicator tip, in this type of solution and just observed underwater. And it's a lot of bubbles formed, indeed. Much more bubbles is formed in the polymers, strangely, okay, and the removal is much faster in polymers, okay. So the reason for that is the following. So cavitation, grazing of material is essentially bubble collapse, which makes a jet coming like that, and this jet hits the surface. Okay, that's the mechanism of grazing of material. So when you have polymer additives, so this essentially is very unstable. Okay, because it's a tiny thing, capillary instability, Rayleigh plateau. When you add polymer, you prevent this jet from breaking. Okay, so this is a hand-waving argument, why suddenly polymer, enhances cavitation instead of decreasing cavitation. Therefore, I would say that, formation of holes, no one studied this, but I did, long ago experiments like that, I did it with Roshkov, who essentially worked, in France, with another group, with Adler, I believe, so France was somehow involved later, much later in that. So you take a target like that, and you essentially issue a jet, impacting the target, and you make the so-called water bells. Okay, Jeffrey Taylor called it water bells. So you can do it with a spoon just in kitchen. Now, why to do that? Because if you have a polymer solution, so when the water bell grows, so there is exactly azimuthal stretching, and polymer should diminish it, and the bell should diminish, and as a result of this diminishing, you essentially can test, rheological models. That's exactly was the motivation. Now, I'll tell you that I've never in these experiments seen any hole formation. However, in normal atomizers with water, I've seen a lot. So, the gut feeling is that this mechanism would be significantly suppressed by polymer, significantly suppressed. Yeah. I would say that let's say you consider this essentially a thermodynamical theory. Okay, you consider an ensemble, okay, and you consider an ensemble without a hole and with a hole, okay, and then the probability comes more or less like the Gibbs probability. Okay, this is exactly the entire thermodynamics. It could be done. So then I would say that the perturbations are coming like independently of us, so they're coming. The question is what they do. And what they do depends on the energy balance. I did this energy balance here, and I showed that there are supercritical, you know, holes which would grow. Okay, now when you have the elastic energy involved, okay, so then you have to revise this calculation, which I didn't do, and take a look, you know, what will happen with the elastic energy added to that. And it might well be, you know, that it will shift a critical hole to that level that it doesn't exist at all. Okay, so that's my more or less gut feelings about that. But I cannot prove it. So. Sure. Yeah. Other questions? Yeah, go ahead.
One question. So in this corona flashing on pre-wetted surface, the point where this thin film disappears, do you see some tiny droplets in that region? I mean, smaller than.
More than the photographs, you know, I showed here, I cannot show anything else. Okay, so, and these photographs were done, like, taken, you know, without my, like, presence. So I'm sorry, I don't know. Okay, but there might be, but how to distinguish them, you know, these are all residual. This all happens on the scale of like 10 to minus 4, 10 to minus 3 seconds. So, so the answer is maybe.
So maybe we thank Professor Yarin again.
Thank you. May I take it off?